Hello everybody and welcome back. Let's talk about the problem majority element. Now, most of the videos on YouTube will try to explain to you the Boyer-Moore algorithm, which is from a class of voting algorithm. However, it is one of those which you need to know beforehand to truly understand it. Plus, if you're given this question in an interview, there is no way you can come up with that on your own. However, I'm going to present another solution. I'm going to present a solution which is super sneaky, something that you can come up with during an interview, and it's not even hard. It's pretty simple and it's right in front of our eyes. Alright, without talking too much, let's go ahead and get started. Alright, so the problem setup says that we're given an array of integers of length n, and the majority element is defined as the element which occurs with greater than n by 2 frequency. The goal of this problem is to find the majority element. So if we look on the right hand side, we see that the input is 322, 422. Clearly the majority element is 2 because it occurs with the frequency of 4. And this frequency of 4 is greater than the required frequency of n by 2, which is 3. Alright, so how can we get started with the solution to this problem? Well, let's talk about the naive solution. What is something that we can do right away? What we can do is create a frequency table. So we can say that 3 occurs with the frequency of 1, 2 occurs with the frequency of 4, and 4 occurs with the frequency of 1. Nothing special, right? We've just created frequencies corresponding to each element. And now what we can do is, after this step 1, we can take the step 2 as going over all of the keys in the dictionary and finding out their values. And if the value is greater than the required frequency of n by 2, well, we can return that as the answer. So in this case, as we iterate over the keys, we look at 3, then we look at 2, and we realize that 2 has a frequency of 4, which is greater than the required frequency of n by 2, 3. So since 2 has a greater frequency, we're going to return 2 as the answer. Pretty simple, right? Nothing too special. Alright, so what's the space-time complexity analysis? Well, order of n space is required for this solution because we're going to store a hash map or a dictionary, which can take order of n time to generate as well. Alright, so we can go ahead and actually look at the code for this, which is pretty damn simple in Python. So from collections, we're going to import counter, and counter is nothing but is going to create us a hash map or a frequency table. And we're going to say counter of a. First of all, go ahead and create that counter, and then use the most common function to get the most common one element. So basically get the highest frequency element. And the rest is just syntax related stuff. And this one-liner solution will get you the correct answer. That is in fact how I was able to solve this in less than 1 minute. But the solution is not the most optimal because we're going to take order of n space. And the follow-up question an interviewer can ask you is that how can you reduce the space? Is there a way to make the space order of 1? Can you make the space constant? Which brings me to the sneaky solution. At this point, other people will go ahead and present to you the Boyer-Moore algorithm. However, there's a better solution that exists right in front of our eyes. Alright, so let's go and take a look at the array again. This is the same array as we've seen before. And the constraint is now written in front of us that we have to do it in order of 1 space. If you think about it, we have to compress the entire hash map. We have to compress sort of the entire dictionary that we created, which took order of n space earlier. We have to compress all of that into somehow just order of 1 space. Sounds pretty weird, right? Impossible, in fact. Here's the thing. Whenever you're stuck in a dead end like this, I've explained this, by the way, in other solutions on my channel as well. Whenever you're stuck in these weird kind of situations where there seems to be no other way and the space constraint is order of 1, you have to think in terms of bits. Go in the binary representations, okay? You don't look at the numbers now as numbers anymore, but they're binary representations. Here's what I mean. Instead of looking at 3, I'm going to look at 3 as 0, 1, 1, which is nothing but the binary representation of 3. Again, I'm not going to change anything. I'm not going to write extra lines of code to convert this. This is just how it is stored in memory. So we're going to write 3 as 0, 1, 1, 2 as 0, 1, 0, and 4 as 1, 0, 0. And I've written this for all of the numbers. Now what I'm going to do is something very interesting. All right, it's something super, super sneaky. I'm going to write answer over here, and we're going to start iterating. Now, if you realize one thing, the majority element is the number which exists with more than n by 2 frequency, right? What it also means is that its binary representation will exist more than n by 2 times, right? Its binary representation itself will have a frequency of greater than n by 2. What I can also say is every single one of its bits will also have a frequency of greater than n by 2. Which means that if we narrow down and if we just look at, say, this particular column, we see a lot of zeros. What does this mean? This means that the majority element has zeros in this place. And that's because this column is overwhelmingly filled with zeros. There is a majority of 0 over here. And remember, we're looking for the majority element. All of its bits are in majority. So what we're going to do is we're going to iterate over all of these columns one by one, and we'll build our answer. Here's what I mean. So we'll look at this column and we'll find out the majority element, which is either 1 or 0. Right? We're not worrying about any frequency tables or hash map right now. I've just flipped the problem on its own head, and now I'm asking, get me the frequency of 1 and get me the frequency of 0. That's it. Just two variables, nothing else. So we can see that the frequency of 0 is overwhelmingly more than the frequency of 1's. In fact, it is greater than n by 2. This means that the answer, the majority element, has a 0 in this particular column's position. All right, what about this particular column? That's right. We see that this column is overwhelmingly filled with 1's, which means that the majority element has 1 in this place. So we're going to write 1 in this answer location. And then we'll iterate over to this column again. And what do we see? There are lots of zeros, not many 1's. The number of zeros is greater than n by 2. So we'll just keep 0 over here. And that is it. So at the end of the iteration, we see that the answer is 0, 1, 0. What is the integer representation of this binary number? That's right, it's 2. We've found the majority element. And look at what we did, right? We just iterated over all of these columns once, and say if the number is represented in 30 bits, we'll just go over this 30 times. So it's like 30 times n, which is the time complexity right now. All right, this will make sense a bit more once we look at the code, but mostly this is the logic. What we are going to do is we're going to iterate over these columns one by one. And then for every single column, we're going to iterate over the numbers and find whether the bit is 1 or 0. And we'll count the number of 1's, we'll count the number of zeros, and we'll be able to guess whether the answer will have 1 or 0 in this place. All right, let's go ahead and look at the code. So we're going to start off with a couple of variables. N is the length of the A, which is something we're going to require very soon. Then we have the answer, which is set as 0. And this is the answer which we are going to return at the end. Right, so as you remember, we start the answer from 0. All right, so now what we're going to do is we are going to iterate over the columns one by one. So we'll say for B in range of 32, that is for every single bit from 0, 1, 2, 3, all the way up till 32, go ahead and iterate over these columns. For each of these columns, I want you to keep a track of the number of 1's in a column, because the number of zeros is simply n minus the number of 1's, right? So we can just keep a track of the number of 1's to get to a solution. And now we'll say, you know what, go ahead and iterate over all the numbers in A. This is an order of n time operation. We'll go ahead and write order of n over here. Now we'll say that, you know what, if 2 to the power of b, this is nothing but 2 to the power of b. If 2 to the power of b and num is true, that is, this entire line means what? This lines mean that the current bit b is set in nums. If the current bit b is set in num, then we can increase the number of 1's by 1. And we'll say that, you know what, at the end of this iteration, if you find that the number of 1's is greater than n by 2, that is, there are overwhelmingly a number of 1's inside of this column, well, go ahead and make this column a 1 as well. So go ahead and set this bit 1 inside of the answer. We can also write this as this OR operation, or we can write it as plus. It's the same either way. Anyways, once we're done with all of those columns, we would have built our answer one by one, and we'll have the answer returned at the end. So we'll go ahead and test this and submit this. Meanwhile, let's talk about the complexity analysis. The space taken is order of 1, since we only ever store a couple of variables. And the time complexity is order of n times log w. Now, I know this log w seems a bit off since we're just doing, 32 total iterations over for the columns. But we have to put this log of w because This 32 is not guaranteed, right? There can be numbers which are huge, which are not stored in 30 or 32 bits. They may take 50 bits or 100 bits or 1000 bits, whatever that is. So we'll just say log of W as the log of the word size. So in this case, integers had a size of like 10 to the power 9, which is approximately 2 to the power 30. So we took 30 times n iterations, right? So it's order of n times log W. Again, I know this is not the most optimal. The time complexity can be order of n and space complexity can be order of 1 with the Boyer-Moore algorithm. However, this is an algorithm that you can come up with even during an interview. And the thing we realized, and the central observation that helped us solve this problem, was that whenever the space constraint is so high, whenever the space constraint is very, very hard, and we're working with these integers and there seems to be no other way out, we have to think in terms of bits. That is the central observation in getting a solution for this problem. This will not only help you for this problem, but other problems as well. So keep this idea in mind for later. All right, anyways, this is it for solution to the problem majority element. If you like this video, give it a thumbs up. These animations, these visualizations take a lot of time for me to create. And if you have any more feedback, let me know in the comment section down below. In any case, this is it for this video solution. And as always, thank you so much for watching.